We had in the last class looked at this Young's modulus versus density plot, and we had indicated that the way we can use this plot to also take into account the fact that shape can be varied is by going ahead and for this particular scenario where you have this original material index that does not take into account shape, if you divide the y coordinate by phi to the power half, if you divide the y coordinate by phi and the x coordinate rho by phi, you have a new material with a combination of properties that exists in this space and allows aluminum, which was initially filtered off from reckoning, to become more competitive. And this was the derivation that we just saw for this material index. Rearranging terms allows you to basically select a new material that takes into account shape. Now we have seen that if you had to compare whether we could get a lighter beam or a heavier beam without paying attention to shape, here was your overall product of function, geometry, and material characteristics. And if the new material that you're considering, keeping the geometry and the loading the same, you had a new combination of density and modulus. You wanted to see what was the weight of the new design. And so M2 over M1 was inversely proportional to the material indices. This was for the stiffness limited design. The same thing could be applied for bending strength as well. How does this criterion then change when we are looking at including shape into the material selection process? So here are a set of materials: steel, aluminum, glass fiber reinforced plastic, and wood. Each of them have different densities. And one criterion could say just based on the density, the lightest material that could be used is wood. But we know that because they all have different modulus, it may not work very well to not only satisfy the stiffness constraint, but also the weight constraint. So it was seen that using this material index e to the power half divided by rho, we could select the lightest material that will satisfy the design constraint. Since you know E and you know rho, you can create another column for this material index for these four materials. Give it a try. So materials for stiff beams of minimum weight, where we fix the shape, choose materials the greatest, E to the power half divided by rho. And so if you take the square root of E divided by rho, you could get these four numbers, which basically indicates that since you're going to select the highest material index, you choose wood. So M of the new material divided by M of steel, which is a reference material, let's say it is equal to 1. Okay. Basically, if you went from steel to aluminum, because it has a higher material index, you basically have a lower mass. If you go to GFRP, since it has a higher material index, you will expect it to be lighter as well. But because wood has the highest material index among the four, you would expect it to be the lightest. This is how we ended up using the case of constant shape and select the best material. Now let us compare the material index where we have a original unshaped mass where phi is 1, and now go to a new shape where you kept the material and geometry the same. The mass of the shaped material relative to the original mass, m0, is the ratio of these two, which basically filters down to phi to the power minus 1 half. So shaping a material at constant bending stiffness reduces the mass of the component in proportion to phi to the power minus 1 half. Let's see how to use this information. This is assuming that the cross-sectional area is the same. Let's take the same scenario of the four materials. We calculated material indices, but now let's say that we've given them shape factor also. You want to be able to make the most efficient shape using each material. You can see based on these kinds of shape factors that steel can be converted into the most efficient shape and wood not much. There's something to pay attention to. That is, the upper limit to which you can improve the efficiency of a material just depends upon the material. Wood cannot be made into as efficient a structure for minimizing mass compared to steel. Just like we had evaluated e to the power half divided by rho as the material index and said materials with the largest value for this material index would be the best choice for minimizing mass. Basically, now we have to go to the fact that phi c or phi max is different for various criteria. And so we have to go by maximizing this modified material index that also includes shape. Do our choices change? Does the best material for minimizing mass, when you take into account the most efficient shape, change the selection?